Hi, MATSE 112. I'm back. After a quick flight across the Atlantic, I'm here in Frankfurt Airport. You can see they have a little work to do on the ceiling. But anyway, it was a good flight, and now I'm back to talk a little bit more about kinetics in electrochemical systems. So this funny looking graph right here, where we're plotting log of I versus potential, right here, shows us different kinetic parts of the dissolution curve of iron in phosphoric acid. So at low potential, you can see that the current goes up very quickly. So there's a peak between negative 0.5 and 0, shown right here. So this peak, so iron corrodes very quickly in phosphoric acid, but then iron forms a passivation layer where the current is very low. And then finally, when you get to high enough potential, the current takes off again. And this describes the oxidation of iron in this electrolyte. So you can see right up here, this is where the conditions are, and these are the different curves shown on the plot, different pHs. So that relationship between current and voltage is decidedly different than what I have drawn here, which is just V equals IR. So that's Ohm's law, and that's a linear relationship between voltage and current. So this is nonlinear for sure. This is Ohm's law. And the difference is that many regular conductors, such as copper wires or even electrolyte solutions or other things that just have resistive losses, show Ohm's law behavior, this linear relationship between voltage and current. However, in reactive systems, or systems where the iron is oxidizing, we often have this sort of behavior where you have corrosion, you have protection, and then finally you have dissolution. So here, the iron is reacting and corroding. We have some passivation layer for iron because this is in phosphoric acid, and so some of the phosphate groups in the acid protect the iron. And then finally, at high enough potential, you have oxidation. So this is where you have reactions occurring, a nonlinear relationship between voltage and current, and V equals IR is just a regular conductor behavior. And this gets us ready to talk about kinetics in electrochemical systems. And so last time we talked about activation energy, and you remember this slide, where we have delta G, and we have the activation energy, and we know we can relate delta G to the electrochemical potential, but now we can relate delta G to E star, or the activation energy, or the activation potential, or the overpotential. And when we have a reactive electrochemical system, we can write the current in this TOEFL relationship. So I is I0 times some exponential. And that eta right there is the overpotential. And so you can see that we have some constants. So I naught is a constant called the exchange current density. RTF and E star are known for the reaction. And then we have E star, which is the overpotential, and then eta as well. And so now this is a nonlinear relationship right here between voltage and current because we have a reactive system. And then finally we get to some linear regime. We won't discuss that too much. But this idea that the current and voltage relationship can be nonlinear is important and is different in a reactive system versus just V equals IR, which is a regular conductor, either an electronic conductor like a wire or an ionic conductor like an electrolyte. So look at these two slides, and we'll have another video on Wednesday. Thank you very much.